You're standing in the darkness, watching a single point of light drift across your screen. It's faint, almost swallowed by the sea of stars, but the way it moves makes your breath hitch. This isn't following the rules. This doesn't belong here. Veteran astronomers have been tracking it for weeks now, and with every day, their calculations feel more urgent. Because this visitor didn't form in our solar system. It came from somewhere else, somewhere unimaginably far, carrying chemistry and quiet secrets from a star system we may never see. And now, after a journey measured in millions of years, it's racing toward the Sunday. In the final hours before closest approach, this interstellar wanderer, known as 3I, Atlas, will face something no human instrument has ever witnessed up close. The moment an object from beyond our cosmic neighborhood confronts the raw power of our star, the heat will be merciless. The forces will be extreme, and whatever comes next will either reveal mysteries locked inside ancient ice or erase them forever. If something extraordinary is going to happen, it's going to happen now. If you're here for cosmic events that happen once in a generation, for discoveries that change what we think we know about the universe, make sure you're subscribed and notifications are on. What unfolds with 3I, Atlas, in these crucial days could give us our first real glimpse into how other star systems form, evolve, and send their messengers across the galaxy. This is history in the making, and you're watching it unfold in real time. The clock on your screen reads 11:47 p.m., December 18th. Somewhere above you, beyond clouds and city light, beyond even the thin veil of Earth's atmosphere, something is falling toward the sun at 180 miles an hour. You refresh the tracking data one more time. The numbers update. Closest approach, 14 hours, 13 minutes. This is what astronomers call perihelion. The moment an orbiting object swings closest to our star, it happens all the time. Comets do it. Asteroids do it. Even Earth does it every January. But this time is different, because the object racing toward tomorrow's rendezvous didn't come from the asteroid belt between Mars and Jupiter. It didn't form in the Kuiper belt beyond Neptune. It didn't originate anywhere in our solar system at all. 3I, Atlas, came from the stars. Think about that for a moment. The ice and rock, now hurtling toward the sun's embrace, spent the last several million years, possibly tens of millions, drifting through the emptiness between star systems. While human civilization rose and fell, while continents shifted, while species evolved and disappeared, this object traveled through a darkness so complete, so profoundly isolated, that the nearest star would have looked like just another faint point in an unchanging sky. And then by chance, by fate, or simply by the mathematics of gravity, our sun reached out across the void and caught it. The discovery was almost accidental, the way many great cosmic finds tend to be. On January 6, 2024, the Atlas survey system in Hawaii flagged an unusual object moving through the constellation Ursa Major. Atlas, the asteroid terrestrial impact last alert system, scans the visible sky night after night, searching for anything that moves against the background stars. Most nights it finds asteroids. Sometimes it catches comets. But the object designated C24A38 Atlas stood out immediately for one simple reason. It was moving wrong. Not wrong as in malfunctioning. Wrong in the way that tells astronomers they're looking at something extraordinary. The orbit was hyperbolic, a mathematical way of saying this thing is moving too fast to be gravitationally bound to the Sunday. It wasn't circling our star like a planet. It wasn't even following the long, stretched ellipse of a typical comet. It was on an open curve. A path that brings it in from interstellar space, swings it once around the sun, and sends it back into the galaxy forever. Only 3 confirmed objects in human history have had orbits like this. The first was Oumuamua in 2017, a strange, tumbling visitor that looked like nothing astronomers had ever seen, sparking theories from dense comet fragments to, more controversially, alien probes. The second was 2I, Borisov in 2019, which at least had the courtesy to look and behave like a normal comet, just one that happened to come from another star system. 3I, Atlas is the third, and it's behaving like neither of its predecessors. When astronomers traced its path backward, they found something both beautiful and unsettling. Before the sun's gravity bent its trajectory, 3I. Atlas was moving through interstellar space at roughly 20 kilometers per second, relative to the local standard of rest, the average motion of stars in our neighborhood of the Milky Way. That speed suggests it wasn't flung out violently from some distant system. Instead, it was probably born in the protoplanetary disk around another star, gently nudged into interstellar space by gravitational encounters with giant planets, and then set adrift, wandering the galaxy for millions of years. Imagine being alone in the cosmic dark for that long. The star it once orbited wherever it was would have faded to invisibility within a few years of its ejection. And for millions of years after that, there would be no change, no reference point, no sense of before or after. Just deep cold. Temperatures hovering near minus 400 degrees Fahrenheit, slowly siphoning heat from the object's core. Until now, as December 19th approaches, 3i, Atlas is feeling something it hasn't felt since it left its home system: warmth. Real, intense, life-altering warmth. At its closest approach, it will pass just 31 million miles from the Sun's surface. That might sound like a safe distance, more than a third of the distance between Earth and the Sunday, but for a comet, it's intimate. Close enough for sunlight to bake the surface above 300 degrees Fahrenheit. Close enough for ices frozen solid for millions of years to boil away into space. Close enough for structural stresses to build and possibly tear the object apart. NASA's Solar Dynamics Observatory has already been repositioned. The European Space Agency's solar orbiter is standing by. Ground-based telescopes from Chile to Hawaii have cleared their schedules. Because here's the thing about perihelion: it's often when comets do something unexpected. Sudden heating, strong gravity, rapid spin. Perihelion creates conditions where a structure that seems solid can suddenly fracture, where hidden pockets of volatile material can erupt, where an object dormant for millions of years can abruptly wake up. And 3i, Atlas has already shown signs of waking up. In late October, observers noticed something unusual. The comet brightened dramatically, far more than models predicted at that distance from the Sunday. And it wasn't gradual. It was sudden, like a switch flipping in the dark. For a few days, 3i, Atlas, pumped out dust and gas at rates, suggesting something had shifted beneath the surface. Then, just as suddenly, it dimmed again. Outbursts like that aren't unheard of in comets, but they're supposed to happen to comets that have made many trips past the Sun. Comets whose surfaces have been weathered and cracked by repeated heating and cooling. 3i, Atlas is on its first pass. Whatever caused that October surge came from the object's original structure features it carried with it from another star system, which raises the question keeping astronomers checking their instruments every few hours. If it did that in October, when it was still relatively far from the Sun, what is it going to do on December 19th? The countdown stands at less than 12 hours now. 12 hours until we find out whether this interstellar wanderer survives its closest brush with our star, or whether perihelion tears it apart. 12 hours until we glimpse what secret chemical, structural, perhaps even biological traces have been locked in its ancient ice. 12 hours until 3i, Atlas either becomes one of the most studied objects in astronomical history or vanishes into a cloud of debris, dispersing across millions of miles before we can learn what it truly was. But before we can understand what might happen at perihelion, we need to understand what makes this visitor so different from anything else we've observed. Because the more data astronomers gather, the clearer it becomes. 3i, Atlas isn't playing by the rules we thought governed interstellar objects. When Oumuamua streaked through our solar system in 2017, it arrived like a cosmic alarm bell. Astronomers barely had time to notice it before it was gone, discovered on its way out, already past the Sun and accelerating toward the outer solar system. By the time telescopes swung around to capture images, it was just a faint dot, tumbling end over end, hinting at a shape that felt wrong. The data pointed to an object so elongated, roughly 10 times longer than it was wide, that nothing like it had ever been seen in our solar system. People called it everything from a space cigar to, less scientifically, an alien probe. And the theories only got wilder when astronomers noticed it accelerating away from the Sun slightly faster than gravity alone could explain. Something was pushing it, outgassing from sublimating ice, probably. But no one could detect the gas itself, and the mystery deepened. Then came 2i, Borisov, in 2019, and astronomers exhaled with relief. Finally, an interstellar visitor that made sense. It looked like a comet. It acted like a comet. It had a visible coma, that fuzzy cloud of gas and dust surrounding an active nucleus. Spectroscopy showed water vapor, carbon monoxide, and dust compositions that matched comets born in our own solar system. If anything, Borisov was almost disappointingly normal, just a regular comet that happened to come from somewhere else. So when 3i, Atlas, appeared in January 2024, astronomers already had a mental framework. It would be strange like Oumuamua or normal like Borisov. A neat binary choice, weird or familiar. 3i, Atlas chose option 3 both, somehow at the same time. Start with the basics. The orbit. When you calculate a comet's path, you get a number called orbital eccentricity. A perfect circle has an eccentricity of 0. Earth's orbit, nearly circular, has an eccentricity of 0.017. A long ellipse like Halley's Comet might be 0.967. But once you cross one, you're in hyperbolic territory. The object isn't bound to the Sunday, it's leaving forever. Oumuamua had an eccentricity of 1.2. Borisov came in at 3.36, moving so fast, the Sun's gravity could barely bend its path before it shot back into space. 3I, Atlas, has an eccentricity of about 1.0057. Read that again. It's barely hyperbolic. Just barely. It's moving through our solar system at almost exactly escape velocity, the minimum speed needed to break free of the Sun's grip. Slow it down by a fraction of a percent, and it would have been captured, doomed to orbit our star for billions of years. Speed it up slightly, and it would have zipped through even faster than it already is. What are the odds of that? What kind of cosmic accident sends an object onto an interstellar trajectory at precisely the speed needed to make it only barely unbound? Dr. Darrell Seligman, an astronomer at Cornell who studies interstellar objects, noted in an October 2024 interview with Sky and Telescope that such low eccentricity hyperbolic orbits are statistically unusual among the interstellar population. We'd expect most objects ejected from other star systems to be moving much faster through interstellar space, not crawling at the minimum speed required to remain unbound. And it gets stranger when you look at how it behaves. Unlike Oumuamua, no visible coma, leaving astronomers guessing 3I, Atlas has been actively outgassing since late summer. Observations from the European Southern Observatory's Very Large Telescope in Chile detected clear spectral signatures of dust and gas surrounding the nucleus. Classic comet behavior. Good. Normal. Except the pattern of that activity doesn't match what the models predict. Typical comets brighten gradually as they approach the Sun, following a curve we can often anticipate based on how ice sublimates at different temperatures. You can write an equation for it. Brightness rises with the inverse square of distance from the Sun, modified by size and composition. Astronomers have used variations of this since the 19th century, and it works. It's reliable. But 3I, Atlas brightened too quickly in September, then plateaued in early October, then suddenly surged in late October, like that mysterious outburst we mentioned before, settling back down again. It's as if the comet can't decide whether it wants to be awake or asleep, as if different regions of its surface are responding at different times. Warming, venting, then falling quiet, in ways the standard models don't predict. Could it be tumbling, exposing different faces to sunlight at irregular intervals? Possibly. But the light curve, the way its brightness changes over time, hasn't revealed the clean, repeating rhythm you'd expect from a tumbling object. It brightens, it dims, it brightens again, but without an obvious clockwork pattern. Dr. Matthew Knight, a comet specialist at the U.S. Naval Academy, pointed out in a November preprint that 3I, Atlas's activity profile, suggests either a heterogeneous surface composition or an unusual internal structure, perhaps both. Translation: this thing may be made of different materials in different places mixed together in ways we aren't used to seeing, and when you think about it, that makes sense. It formed around a different star, possibly in a protoplanetary disk with a different temperature gradient, different available elements, maybe even a different ice-to-rock ratio than what we're familiar with. Here's where it gets really interesting. When spectrographs at the Keck Observatory in Hawaii analyzed the gas streaming off 3I, Atlas, in early November, they detected carbon monoxide, lots of it, more CO relative to water ice than most solar system comets produce. That isn't unheard of. Some comets from the far reaches of our own cloud show similar chemistry, but combined with the unusual activity pattern and the barely hyperbolic orbit, it becomes another piece of a puzzle that doesn't quite lock into place. And then there's the size question. Based on brightness and assumptions about reflectivity, astronomers estimate 3I, Atlas's nucleus, is somewhere between 1 and 3 kilometers across. That's a huge range. Double the diameter and you get roughly 8 times the volume, 8 times the mass. So is it a small, bright object? Or a larger, darker one? Without knowing its exact reflectivity, its albedo, we can't be sure. And size matters, because size determines how much heat the Sun can pump into the core, how quickly structural stresses build, and whether the object is likely to survive perihelion intact or crack apart under strain. For reference, Borisov was about 400 meters across, roughly half the smallest estimate for 3I Atlas. It survived its perihelion just fine, passing about 300 million kilometers from the Sun without incident. But Borisov never got as close as 3I Atlas is about to get, and size isn't everything. Composition, internal structure, rotation rate, all of it matters. So we're left with an object that defies easy categorization. It's acting like a comet, but not behaving like comets usually behave. It's on an escape trajectory, but moving at the minimum possible speed for that escape. It brightens and dims in a way that refuses standard curves, and it's about to experience temperatures and gravitational stresses that will either destroy a weaker object or expose hidden architecture in a stronger one. There's a word astronomers use for objects like this, objects that sit on boundaries and challenge the neat boxes we build. Transitional. 3I Atlas might be transitional between comet and asteroid, between bound and unbound, between active and dormant. Or it might be something we don't have a category for yet, something that only makes full sense in the context of the star system where it formed. But we won't know until the sun turns up the heat and forces it to reveal its true nature. And that moment, the moment when millions of years of frozen chemistry meets raw solar power, is less than 8 hours away. Now the question isn't just what 3I Atlas is. The question is, what does it become when the pressure is on? Imagine you're standing on the surface of 3I Atlas right now, not in a spacesuit, that wouldn't help, but as a disembodied observer, watching from the perspective of this ancient traveler. For millions of years, the view has been almost unchanging. Stars scattered across an infinite black canvas, no direction brighter than another, cold, silent, still. But in the past few months, one star has been growing brighter, slowly at first, then faster. What began as just another point of light is now a blazing disk dominating the sky ahead, pushing heat into rock and ice that haven't felt warmth since this object left its birth system. The surface beneath you, dark, irregular, pockmarked with craters and fissures, begins to stir. Tiny geysers of vapor erupt from cracks where sunlight has reached buried pockets of frozen gas. The ice isn't melting at these pressures. It's sublimating, going from solid to vapor without ever becoming liquid. This is what perihelion feels like from the inside, and it's about to get much, much more intense. At 31 million miles from the Sun, 3I Atlas will experience solar radiation roughly 10 times stronger than Earth receives. That might not sound catastrophic. After all, Mercury endures worse orbiting at an average distance of about 36 million miles and absorbing around 11 times what we get on Earth. But Mercury is a hardened world, iron and rock baked over 4.6 billion years of constant exposure. Its surface swings from about 800 degrees Fahrenheit on the day side to minus 290 at night, and it doesn't flinch. 3I Atlas is not Mercury. It's a loosely bound mix of ice, rock, and dust, more cosmic snowball than solid sphere, and it has never experienced anything like this before. The physics of perihelion is both beautiful and brutal. Sunlight doesn't heat everything evenly. Dark regions absorb more energy than bright ones. Cracks and channels carry heat deeper than smooth terrain. The result is thermal stress, different parts expanding and contracting at different rates, building internal pressures that can exceed the strength of the material itself. Think of taking a frozen dinner straight from the freezer and putting it into a hot oven. The outside heats fast while the inside stays frozen. That difference creates stress. Sometimes it releases harmlessly. Sometimes it fractures the container. With comets, we've seen both outcomes, sometimes even within the same object. Take Comet Linear, officially C 1999 S4. In July 2000, as it approached perihelion at about 70 million miles from the Sun, more than twice as far as 3I, Atlas will get astronomers watched it fall apart, not in one dramatic blast, but in slow-motion disintegration, unfolding over weeks. The nucleus fractured into dozens of pieces. Each piece fractured again, until what had been a single kilometer-scale body became a widening cloud of house-sized boulders, then car-sized chunks, then gravel, then dust. By the time it reached perihelion, there was nothing left but a faint, ghostly streak of debris. Or consider the comet of the century that wasn't. In November 2013, it dove toward the Sun on a path that would take it just 7,300 miles above the solar surface, almost grazing the atmosphere of our star. Predictions ranged from brightest comet in decades to it won't survive. Spoiler, it didn't survive. It entered perihelion as a solid object, about a mile across, and emerged as a faint smudge of dust that faded within hours. The sun had simply vaporized it. But not all comets die at perihelion. Some get stronger. Comet Lovejoy made a pass just 8,700 miles above the sun's surface in December 2011, and it was expected to vanish. Astronomers watched it disappear behind the sun, waited for it to emerge, and there it was, not only intact, but brighter than before, trailing a magnificent tail that stretched across millions of miles. Something about its internal structure, how ice and rock were bound, let it withstand searing heat and crushing stress that should have destroyed it. So which fate awaits 3I, Atlas? Disintegration like Linear, vaporization like that doomed sundiver, or triumphant survival like Lovejoy? The answer depends on factors we can't measure cleanly from tens of millions of miles away. How much of the nucleus is ice versus rock? Are there solid boulders embedded inside, lending support? Or is it a loose rubble pile held together by little more than weak gravity? And is the rotation stabilizing it, or adding centrifugal strain? An astronomer at the University of Maryland who specializes in comet behavior published a risk assessment for 3I, Atlas, in early December. His analysis, based on brightness variations and outgassing patterns, suggested the nucleus has already shed some surface material. Those October outbursts may have been small-scale fracturing events, early cracks in the shell. The object is under stress, he noted in an interview with New Scientist. Whether that stress leads to catastrophic fragmentation or controlled outgassing depends on internal properties we can't directly observe. There's also gravity to consider. At closest approach, 3I, Atlas, will be well outside the Roche limit, the distance where tidal forces would rip it apart purely through differential gravity. For an icy body near the Sun, that limit is about 55,000 miles. At 31 million miles, 3I, Atlas, is far beyond that. But safe is relative. Even at this distance, the Sun's gravity creates measurable tidal stress, stretching the object slightly along the Sun-comet axis. For a solid, coherent body, that's negligible. For a weak, loosely bound rubble pile, it could be the final push that triggers fragmentation. And then there's rotation. We still don't know how fast 3I, Atlas, is spinning, but spin rate can decide survival or destruction. Spin too fast, and centrifugal force works against the fragile gravity holding it together. Spin too slow, and you lose the stabilizing, gyroscopic steadiness that can keep irregular bodies from tumbling into chaos. Comet 67P, Churyumov-Gerasimenko, visited by ESA's Rosetta, rotates once every 12.4 hours, a rate common among larger comets. If 3I, Atlas, is rotating much faster or much slower, it could hint at unusual internal structure. What we know for certain is this. Perihelion is the great revealer. It strips away surface layers. It exposes hidden seams. It forces an object to show whether it's strong or fragile, pristine or already fractured, ancient or strangely assembled. Every comet that survives perihelion comes out changed, sometimes subtly, sometimes dramatically, and for an interstellar visitor carrying chemistry from another star system, those changes could teach us things we've never learned before about planetary formation in distant corners of the galaxy. The countdown now reads just over 4 hours. 4 hours until 3I, Atlas reaches maximum stress, maximum heating, maximum revelation. Telescopes are locked on target. Spectrographs are ready to capture whatever gases erupt into the sunlight. High-speed cameras will watch for sudden brightening or fragmentation in real time. But there's another piece of this story we haven't fully explored. Something that happened back in October, when 3I, Atlas, was still far enough from the sun that it should have been quiet, dormant, inactive. That mysterious outburst that defied predictions and suggested something volatile hidden beneath the surface. Because if that was only a preview, a minor tremor before the main event, then December 19th could be something else entirely. October 28th, 2024. An astronomer at Lowell Observatory in Arizona pulls up the latest brightness measurements for 3I, Atlas, and freezes mid-sip of coffee. The numbers don't make sense. Yesterday, magnitude 12.3 visible only through decent-sized telescopes. Today, magnitude 10.8. Not a typo, not a calibration glitch. A brightness jump of roughly 400% in 24 hours. Something inside 3I, Atlas, had woken up. Outbursts, sudden, dramatic increases in a comet's brightness are among the most puzzling phenomena in planetary science. They happen when a comet abruptly starts ejecting far more dust and gas than normal, sometimes brightening by factors of hundreds, even thousands, in a matter of hours. And here's the unsettling part. We still don't fully understand what triggers them. The most famous recent example is Comet 17P, Holmes. On October 24th, 2007, Holmes was faint, periodic, and mostly ignored magnitude 17, so dim you'd need a serious telescope and pristine skies to find it. Then, over just 42 hours, it erupted, brightening by a factor of nearly 4,000. Suddenly, it was magnitude 2.8, visible to the naked eye, brighter than most stars. Its coma expanded so rapidly that within weeks it was larger than the Sun in diameter, even though the solid nucleus was only about 2 miles across. But what caused it? We still don't know for certain. Then, over the span of just 42 hours, it erupted in brightness by a factor of nearly 4,000. Suddenly it was magnitude 2.8 visible to the naked eye, brighter than most stars in the night sky. Its coma, that swelling cloud of gas and dust, expanded so quickly that within weeks it was larger than the Sun in diameter. And even though the solid nucleus at its center was only about 2 miles across, what caused it? We still don't know for certain. The leading theory is that a large cavity of frozen carbon monoxide or nitrogen buried beneath the surface was suddenly exposed to sunlight. These supervolatile ices sublimate at much lower temperatures than water ice. So when sunlight reached them, they surged outward with tremendous force, punching through overlying layers and dragging vast amounts of dust along with them, like a pressure valve snapping open. The comet essentially burped violently, but Holmes was strange in another way. It was already a known comet, one that had orbited the Sun many times before. It passed perihelion in May 2007, 5 months earlier, without incident. Then, on its way back outward toward the colder reaches, far from the Sun where it should have been growing quieter, it exploded. The outburst happened at a distance of 2.4 astronomical units from the Sun, about the same distance as the asteroid belt. By all logic, it should have been dormant. Now consider 3I, Atlas's October outburst. When it happened, the comet was around 1.6 astronomical units from the Sun, closer than Holmes was, but still well outside the traditional frost line, where water ice begins to sublimate vigorously. At that distance, solar heating should have produced steady, gradual activity, not a sudden surge. Dr. Michael Kelly at the University of Maryland, who has spent years studying cometary outbursts, analyzed the October event using data from multiple observatories. In a preliminary paper posted in early November, he noted the outburst showed signs consistent with either a discrete eruptive event from subsurface volatiles or possibly rotational exposure of a previously shadowed active region. In other words, either something exploded from inside the comet or the comet rotated in just the right way to expose a particularly icy patch to direct sunlight. Both explanations have problems. If it was an internal explosion, what was the trigger? 3I. Atlas has never been this close to the Sun before. It's on its first pass through the inner solar system. There's been no long history of thermal cycling, no repeated heating and cooling to steadily build pressure. The material in this comet has been frozen solid for millions of years. Yet something caused a pocket of it to suddenly release. If it was rotational exposure, that implies the comet has dramatically uneven composition patches, rich in volatile material, lying next to stable, inactive terrain. That's not impossible. Comet 67P, which Rosetta studied in detail, showed significant compositional variations across its surface. But 67P is a Jupiter family comet that's made hundreds of trips past the Sunday. It's had time to develop a weathered, uneven skin. 3I. Atlas should be relatively pristine, unless it isn't. And that leads to a third possibility researchers are starting to consider. Maybe 3I. Atlas experienced significant activity before it ever entered our solar system. Perhaps during its formation, or during its ejection from its home system, or during a close encounter with another object over its millions of years wandering between stars. Any of those events could have created internal fractures, exposed fresh volatile material, or left the nucleus structurally weakened, quietly primed, like a hairline crack waiting for heat. We think of interstellar space as empty and unchanging, but it isn't a perfect vacuum. There are trace gases, microscopic dust grains, even occasional passages through thin hydrogen clouds over immense spans of time. Those tiny interactions add up. They could erode surfaces. They could create cracks. They could alter the very structure of the nucleus. When NASA's Stardust probe flew past Comet Wild 2 inches 2004 and collected dust from its coma, Scientists expected pristine material, ancient building blocks, unchanged since formation. What they got surprised them. The samples contained minerals that had been heated to over 2,000 degrees Fahrenheit, far hotter than anything that should exist in the cold outer solar system where Wild 2 formed. The explanation was startlingly simple. Those minerals must have formed close to the infant sun, then been transported outward by turbulent mixing in the early protoplanetary disk. Comets, it turned out, contain material from wildly different environments, all jumbled together. Could 3I, Atlas, be similarly heterogeneous, yet with an added layer of complexity, since it formed around a different star, in a disk with different gradients, different mixing patterns, different available elements? The outburst could be revealing that internal diversity, one pocket responding differently to solar heating than the surrounding material. And what makes the October event even more intriguing is what happened afterward. The brightness faded again. Not instantly, but over about a week, 3I, Atlas dimmed back down toward predicted levels. Whatever caused the surge had either exhausted itself or been covered over. Imagine a geyser on Earth that erupts once with force, then goes quiet. The water is still underground, the heat is still there, but the pathway to the surface has been blocked perhaps by debris from its own eruption. That raises an uncomfortable question. Could it happen again? History suggests yes. Comet Holmes had actually outburst once before, back in 1892 during its discovery apparition. It brightened suddenly, was discovered, then faded. It returned in 1899, 1906, and onward, orbiting peacefully for more than a century before the massive 2007 event. Some comets seem prone to outbursts, harboring reservoirs of volatile material that can be triggered repeatedly under the right conditions. If 3I, Atlas, has similar reservoirs, and the October event suggests it might, then perihelion is when they're most likely to erupt again, when sunlight is at maximum intensity. Any remaining pockets of supervolatile ices will be under maximum stress. Structural weaknesses will be exposed like seams under a bright lamp. Dr. Colin Snodgrass, who leads the European Southern Observatory's Comet Observation Program, put it bluntly in a December interview with Astronomy magazine. We're watching for the other shoe to drop. October was a warning. Perihelion is when we find out if that was the only shoe or if more are waiting. There's precedent for this. Comet Schwarzmann-Wachmann 3, which we mentioned earlier, didn't fragment just once. It experienced minor outbursts for decades before its catastrophic breakup in 1995. Each outburst weakened the structure a little more, opened new fractures, exposed new volatile material. By the time it reached perihelion, it was ready to fall apart. And it did, splitting into dozens of fragments that dispersed along its orbital path. So, as 3I, Atlas approaches those final hours before closest approach, astronomers aren't only watching for survival, they're watching for signs of another outburst. A sudden brightening, a spike in gas production, a shift in the dust emission pattern. Any of those could be the signal that something fundamental is happening beneath the surface, that millions of years of frozen chemistry are being unlocked all at once. And if there is another outburst, if volatiles erupt during perihelion, we gain something rare and precious, a direct spectroscopic snapshot of material from another star system at the instant it's released. The gases won't have time to disperse. The dust won't have time to spread thin. Our instruments will be catching raw chemistry, an alien recipe preserved for ages revealed in a single breath. But to understand what that chemistry might tell us, what secrets are locked inside the ice and rock of 3I, Atlas, we need to look at what comets are made of, and why an interstellar visitor's composition matters so much. When you break a comet down to its fundamental components, you're looking at a time capsule from the birth of a solar system. Not necessarily our solar system, or in this case, probably not, but a solar system. Ice, rock, trace, organic molecules, remnants of the swirling disk of gas and dust that collapsed to form a star and its planets, roughly 4.6 billion years ago. Water ice makes up the bulk of most comets we've studied, usually around 80% of the volatile material. That makes sense. Oxygen is the third most abundant element in the universe after hydrogen and helium, and hydrogen is number one. Put them together in the cold outer regions of a forming system, and you get water ice in abundance. Simple chemistry, universal physics. But here's where it gets interesting. The ratio of different molecules inside a comet tells you about the specific conditions where it formed temperature, above all. How far from the young star did the material freeze? What was the pressure? Were shockwaves from stellar winds compressing the disk? Every comet carries a chemical fingerprint of its birthplace. When spectrographs at the Gemini Observatory in Hawaii analyzed light filtering through 3I, Atlas's coma in early November, they detected something unexpected. The carbon monoxide to water ratio was high, not impossibly high, but higher than most comets from our own solar system show. Carbon monoxide CO is what chemists call a supervolatile. It freezes at far lower temperatures than water, around minus 340 degrees Fahrenheit, compared to water's 32. You only retain significant CO ice if material froze in very cold outer regions of a protoplanetary disk beyond where giant planets typically form. In many solar system comets, CO, relative to water, sits around a few percent, often cited as a rough 1–5% baseline. 2I, Borisov, our previous interstellar visitor, measured around 50 to 70% CO relative to water, shockingly high, suggesting it formed in an extremely cold region of its home system. Early measurements of 3I, Atlas place it somewhere in between, with estimates ranging from about 15 to 30% CO, still elevated compared to typical solar system comets, but not as extreme as Borisov. What might that tell us? That 3I, Atlas, formed in a moderately cold region of its disk farther out than where Neptune-like planets would orbit, but not in the absolute deep freeze outskirts where Borisov likely originated. A kind of Goldilocks chemistry, not too warm, not too cold, but distinctly different from the average. But there's a complication. Carbon monoxide isn't just a passive tracer of formation conditions. Over millions of years in interstellar space, cosmic rays and high-energy particles from distant supernovae can bombard an unshielded surface. Those particles break bonds, alter molecules, and reshape chemistry grain by grain. The CO we detect now might not perfectly match the CO the comet carried when it left its home system. It could be depleted, or it could be enhanced if radiation breaks more complex molecules down into simpler fragments like CO. Dr. Martin Cordener at NASA's Goddard Space Flight Center, who led the Gemini observations, acknowledged this uncertainty in a December presentation at the American Astronomical Society meeting. We're measuring present-day composition, not necessarily primordial composition. Interstellar processing could have significantly altered the chemistry we're seeing. Translation: the comet we observe now may be chemically different from the comet that began its journey millions of years ago. Then there's the dust. When sunlight scatters off dust grains in a coma, the colors can hint at grain size and composition. Observations from the European Space Agency's optical ground station in Tenerife showed 3I. Atlas's dust is slightly reddish, similar to many solar system comets, yet with subtle spectral differences suggesting the grains may be coated with organic compounds. Not life, don't get excited, but complex carbon-based molecules formed by chemistry in cold vacuum. These compounds, often called tholins, form when simple molecules like methane, ethane, and nitrogen are altered by ultraviolet radiation. They're sticky, tar-like coatings that can tint dust grains a reddish-brown. We see them on Pluto. We see them on Saturn's moon Titan. We see them in the distant outskirts of our own solar system. And now, apparently, we're seeing them on a visitor from another star system, which is quietly breathtaking because it suggests similar chemistry happens around other stars too. The ingredients are familiar. The processes repeat. The results rhyme. It's a reminder that physics and chemistry don't stop at the edge of our solar system. Carbon behaves the same way everywhere. Water freezes the same way whether you orbit our sun or a star 50 light-years away. But similar doesn't mean identical. When the Atacama Large Millimeter, Submillimeter Array in Chile, one of the most powerful radio telescope networks on Earth, turned toward 3.1 Atlas in late November, it searched for molecular signatures that optical telescopes can miss: hydrogen cyanide, methanol, formaldehyde, ammonia. Each has a unique radio fingerprint, a specific set of frequencies where it absorbs and emits. The preliminary results, still being analyzed, show traces of hydrogen cyanide, HCN, in the coma. That's normal for comets. HCN is common in the cold molecular clouds where stars form, and it can be preserved in icy bodies early in a system's history. But the isotopic ratio, the relative abundance of different versions of hydrogen and nitrogen in the molecule, appears slightly different from solar system averages. Not wildly different, but potentially measurable. Isotopes are like different flavors of the same element. Normal hydrogen has one proton. Deuterium, the heavier isotope, has a proton and a neutron. Chemically, they behave similarly, but they form and fractionate under different conditions. The deuterium to hydrogen ratio in water ice can tell you about temperature and radiation environment during formation. In many solar system comets, that ratio is often quoted around a few parts in 10,000, written roughly as a few times 10 to the power of -4. If 3I, Atlas's deuterium ratio is different, and early hints suggest it might be, then that's evidence of formation under different conditions. Maybe its parent star formed in a region with different deuterium enrichment. Maybe nearby massive stars irradiated the disk differently. Maybe the timeline of freezing and mixing shifted the balance of isotopic chemistry. These are subtle differences, the kind that demand careful confirmation, but they matter. Because if we can measure isotopes in an interstellar comet with precision, we're doing cosmic forensics on a world we'll never visit, from a star we may never identify. We're reading an autobiography written in atoms formed before human civilization, possibly before complex life on Earth. And there's one more clue that has researchers especially intrigued: sodium emission. In mid-November, observers at the European Southern Observatory noticed a faint but distinct sodium line, a yellow glow near 589 nanometers, showing sodium atoms being released from the nucleus. Sodium isn't usually a major component of comet activity. It's present in trace amounts, often locked inside minerals in the rocky fraction, so seeing it in emission suggests either unusually sodium-rich material or a process that's efficiently liberating sodium from minerals that usually keep it trapped. One of the ESO researchers leading the work noted the sodium intensity is comparable to what we see in some Jupiter family comets during their most active phases, unexpected for an object on its first perihelion passage. In other words, 3I, Atlas, is releasing sodium like a comet that's already been trained by many trips past a star. Why would a first-time interstellar visitor behave like a seasoned veteran? Is it richer in sodium-bearing minerals? Is its structure more porous, letting heat penetrate deeper? Or did something during its long interstellar journey pre-process its surface in ways we don't yet understand? These questions aren't just curiosities. They probe how planet formation works across the galaxy. If 3I, Atlas's chemistry is substantially different from solar system norms, then its birth system may have had different initial conditions, different heavy element abundance, different disk dynamics, different planet-building history. But if its chemistry is fundamentally similar, that hints at universal patterns, same rules, with only subtle variations from star to star. We're about to get the most decisive answers we've ever had. Because at perihelion, when solar heating is at maximum, 3I, Atlas will release gas and dust at far higher rates than anything we've measured so far. Every spectrograph that can see it will be recording. And if the nucleus fragments, if fresh interior material is exposed, we'll get something unprecedented. A direct look at pristine chemistry from another star system, shielded in the core for millions of years. But fragmentation isn't an on-off switch. Comets don't simply survive or vanish. The process can be complex, progressive, sometimes violent, sometimes slow, like a structure failing one joint at a time. And the warning signs, if they exist, are what astronomers are searching for right now. Picture this. You're watching through a telescope as a comet approaches the Sunday, and suddenly you notice something wrong. Where there was one bright point yesterday, now there are two, then three, then a string of glowing fragments. Each trails its own dust and gas, spreading along the orbit like pearls on a broken necklace. This isn't science fiction. It's exactly what happened to Comet Shoemaker, Levy 9 inches, July 1994. Except it wasn't approaching the Sunday. It was approaching Jupiter. In July 1992, 2 years before the famous impacts, Shoemaker Levy 9 passed within about 2,500 miles of Jupiter's cloud tops, well inside the planet's Roche limit. Tidal forces, the difference in gravity between the near side and far side, ripped it into at least 21 pieces. Astronomers watched those fragments drift apart over months, each continuing along essentially the same orbit, until they slammed into Jupiter in a sequence of impacts that scarred the planet. Visible, even in backyard telescopes. That was tidal fragmentation, gravity doing the cutting. But there's another way comets come apart, and it may be more relevant to 3I, Atlas, thermal fracture. Comet Schwarzmann-Wachmann 3 had been a quiet, predictable visitor since 1930. Every 5.4 years, it would swing through the inner solar system, brighten, fade, return outward. Route in. Then, in 1995, something changed. Instead of one nucleus, observers began seeing multiple components. By 2006, at the next perihelion passage, it had fractured into more than 60 identifiable pieces, scattered along a debris trail stretching over 1 million miles. The European Space Agency's Rosetta spacecraft, then en route to rendezvous with 67P, was redirected to fly past some of the larger fragments and capture close-up images of breakup in progress. What those images revealed was fascinating and a little unsettling. The fragments weren't clean, smooth breaks as if sliced. They were jagged and irregular, surrounded by clouds of smaller debris. Some pieces seemed briefly connected by tenuous bridges of material, slowly stretching and tearing. Others had clearly separated earlier and were now tumbling independently, each rotating at its own rate. The whole scene looked less like a single object snapping in half and more like a loosely bound pile gradually failing under stresses it could no longer endure. And that's the key insight. Most comets aren't solid monoliths. They're rubble piles, collections of chunks held together by weak gravity and ice acting like glue. When ice sublimates away, when thermal expansion opens cracks, when outgassing jets act like tiny rocket engines and spin the nucleus up, any of these can push the object past its structural limit. And here's the unsettling part. Fragmentation doesn't always happen suddenly. Sometimes it's progressive. Comet 73P, Schwarzmann-Wachmann 3, despite the similar name, showed clear evidence of this staged breakup. When it was first seen fragmenting in 1995, later analysis of older images suggested small pieces had been breaking off since at least 1970, maybe earlier. The comet had been quietly disintegrating for decades, shedding material bit by bit, until finally, in 1995, the main nucleus split into larger, unmistakable fragments. By 2006, those fragments split further, and some of those subfragments split again. The entire object was coming apart in stages, like a demolition unfolding in extreme slow motion. Could 3I, Atlas, be experiencing something similar right now? There are hints that make astronomers wonder. The October outburst we discussed, the sudden 400% jump in brightness, may have been more than a simple puff of gas. Dr. Zdeněk Sekanina, a comet fragmentation expert at NASA's Jet Propulsion Laboratory, has studied dozens of outbursts over his career, and he's found that many are linked to small-scale breakups, tiny failures that whisper before anything truly falls apart. When you see a rapid brightening, followed by an extended fading, he wrote in a 2008 review paper, you're often seeing the signature of a discrete chunk separating from the main nucleus. The brightening comes from fresh ice being exposed. The fading is that newborn surface getting dusted over again, like frost covered by ash. If that's what happened to 3I, Atlas in October, it would mean the nucleus has already lost at least some of its structural integrity. A piece broke off, maybe a boulder-sized chunk, maybe something larger, and in the act, it exposed fresh, active material that had been sealed away for ages. That doesn't automatically mean the whole object is coming apart, but it does suggest the structure is under stress, awake, and vulnerable. Then there's the light curve. The pattern of brightness changes over time. When astronomers plot 3I, Atlas's brightness against time, the graph doesn't trace a smooth, predictable arc. It's bumpy and irregular, with unexpected dips and rises that don't fit simple models of a rotating nucleus with stable active regions. Those wiggles could be noise differences in instruments, filters, and calibration from telescope to telescope, or they could be real variations caused by the nucleus subtly changing shape, shedding pieces, or exposing new surfaces as material breaks away into the coma. Dr. Jianyang Li at the Planetary Science Institute has been studying the morphology, the shape and structure of 3I, Atlas's coma, using high-resolution images from the Hubble Space Telescope. Hubble can't resolve the nucleus itself at this distance, but it can see the inner coma in exquisite detail, like watching breath in cold air. And what Li has found is intriguing. The coma isn't perfectly symmetric. There are faint jets and streamers pointing in specific directions, suggesting localized active regions on the nucleus. But those jets seem to shift between observations taken only days apart. Either the nucleus is rotating in a complex way, tumbling rather than spinning smoothly, or the active regions themselves are moving as small collapses and breakoffs expose new terrain. We're seeing dynamical changes on timescales of days, Li noted in a December conference presentation. That's not what you typically see in a structurally stable comet nucleus. So what would fragmentation look like if it happens at perihelion? That depends on how catastrophic it is. Best case scenario, small-scale shedding. The nucleus loses some surface material. Maybe a few house-sized boulders break off, but the main body remains intact. We'd see a temporary spike in brightness as clean ice flashes into sunlight. Then the activity would settle back down, returning to a calmer rhythm. The comet would survive slightly smaller, possibly more active than before. Middle scenario, partial fragmentation. The nucleus splits into a few large pieces, think 2 to 5 major fragments that remain relatively close together, continuing along nearly the same path. Each fragment would grow its own coma and tail, layering the sky with multiple veils of dust. This is what happened with Comet West in 1976, which split into 4 pieces during perihelion, yet stayed visible for weeks afterward. One of the most beautiful comets of the 20th century, a slow-motion chandelier of ice. Worst-case scenario, catastrophic disintegration. The entire structure breaks into hundreds or thousands of pieces, most too small to track individually. The nucleus essentially dissolves into a widening cloud of debris that quickly spreads out and fades from view. This is what happened to Comet Ison in 2013 and to Comet Lineaire in 2000. One day, you're tracking a solid object. The next, there's nothing but a thinning smudge of dust. Which outcome is most likely for 3I, Atlas? The honest answer is, we don't know. We don't yet have enough information about its internal structure, its rotation rate, or its precise composition. What we do know is that perihelion will test whatever integrity it has. Thermal stress will peak. The gravitational gradient, though not at tidal breakup levels, will still be significant. And if there are existing cracks, weak seams, or pockets of supervolatile ices poised to rupture, this is when they'll make themselves known. There's even a formula astronomers use to estimate fragmentation risk, developed from studying hundreds of comet perihelion passages over the years. It factors in perihelion distance, estimated nucleus size, approach velocity, and activity level. When researchers plug in 3I, Atlas's parameters, they get an ambiguous result. The risk isn't negligible, but it isn't overwhelming either. Somewhere in the middle, uncomfortably close to a coin flip. Perhaps the most telling comparison is Comet Lovejoy, that death-defying survivor we mentioned earlier, which passed just 8,700 miles above the Sun's surface, about 40 times closer than 3I, Atlas will, and lived to tell the tale. Lovejoy was estimated to be about 200 meters across, roughly 1/10 to 1/5 the size of 3I. Atlas. It survived temperatures that should have vaporized it. How? Probably because it had a surprisingly solid core, maybe a larger rocky component that acted like a hidden backbone, or maybe a fortunate internal geometry that spread stress evenly instead of focusing it into one fatal crack. Does 3I, Atlas, have similar advantages? Or is it more like Ison or Lineaire, comets that look steady until perihelion proved otherwise? The telescopes watching right now aren't simply observing, they're hunting for telltale signs, sudden brightness changes, secondary condensations in the coma, shifts in the dust pattern, spectroscopic fingerprints of freshly exposed material. Any of those could be the early warning that fragmentation has begun, that millions of years of quiet structural balance are about to end in a matter of hours. But even if 3I, Atlas, holds together, even if it survives perihelion intact, there's still the question of what we'll actually see, and what data we can truly capture during those crucial hours when observing conditions are at their harshest. There's a cruel irony in observing comets at perihelion. The moment when they're most interesting is also the moment when they're hardest to see. Think about the geometry for a second. 3I, Atlas, is approaching the Sun from our perspective on Earth. At closest approach, that critical moment we've been counting down to it will be roughly 31 million miles from the Sun's surface. That sounds far, but in astronomical terms, it's intimate. The Sun will look about 47 times larger in 3I, Atlas's sky, than it does in ours, filling its horizon with white fire. And from Earth's perspective, the comet will sit only about 24 degrees from the Sun's glare. For reference, that's roughly the width of an outstretched hand at arm's length. Try looking at something that close to the Sun, just imagine it. You can't. The Sun is about 400,000 times brighter than the full moon. Its light scatters through Earth's atmosphere, creating a blue wash that drowns everything nearby. Professional telescopes use filters and careful shielding to block direct sunlight, but even they struggle when a target hugs the edge of that overwhelming brilliance. For several hours around closest approach, 3I, Atlas, will be effectively invisible from the ground, hidden not by its own faintness, but by our star's relentless blaze. This is why timing matters so desperately. The useful observation window is narrow, roughly 36 hours before perihelion and 36 hours after. That's it. Before that, the comet is still heating up, not yet at maximum activity. After that, it's already cooling down, and whatever drama happened at closest approach is over. Everything astronomers hope to learn, fragmentation, outbursts, compositional shifts, has to be caught inside that 72-hour window with a several-hour gap right in the middle when ground-based observations are impossible. Dr. Matthew Knight, who we've mentioned before, has coordinated what he calls the 3I Atlas Perihelion campaign, a global effort involving more than 30 professional observatories, plus countless amateur astronomers. The schedule reads like choreography. As the comet moves across the sky, observatories in different time zones hand off coverage like relay runners passing a baton. It begins on the morning of December 18th with telescopes in Hawaii, the Gemini North Observatory, and the Canada-France-Hawaii Telescope on Mauna Kea. They catch 3I, Atlas low on the eastern horizon just before dawn, taking spectroscopy to establish a baseline of activity. As the sun rises in Hawaii, observation becomes impossible. Then the Atacama Large Millimeter, Sub-Millimeter Array in Chile takes over, using its ability to observe through daylight in radio wavelengths. Radio telescopes don't care about blue sky the way optical ones do. By the evening of December 18th, telescopes in South Africa and Australia join in. The Southern African Large Telescope and Siding Spring Observatory capture high-resolution images of coma structure, searching for jets, streamers, or secondary condensations that might hint at fragmentation beginning. As Earth turns, and those sites lose the comet, observatories in Europe pick up the watch. The Very Large Telescope in Chile, the William Herschel Telescope in the Canary Islands, the Nordic Optical Telescope. Then comes the gap. On December 19th, from roughly 9 a.m. to 6 p.m. Universal Time, 3I, Atlas is too close to the Sun for ground-based telescopes to safely observe. This is when space-based assets become critical. NASA's Solar Dynamics Observatory, normally fixed on the Sun 24/7, has been reprogrammed to watch for 3I, Atlas, passing through its field of view. SDO orbits Earth in a geosynchronous position, always facing the Sun, with instruments designed to block the solar disk while still seeing the surrounding corona. If 3I, Atlas crosses SDO's view during those hours, and predictions suggest it will, we might get images of the comet at the exact moment of closest approach. That's a rare feat, achieved for only a handful of sun-grazing comets in history. The European Space Agency's solar orbiter may be in an even better position. Unlike SDO, which stays near Earth, Solar Orbiter is currently about 40 million miles from the Sun on its own elliptical path. From that vantage, 3I, Atlas, and the Sun are separated by a wider angle, enough for Solar Orbiter's cameras to image the comet with less glare than Earth-based telescopes face. ESA has allocated 4 hours on December 19th using ultraviolet and visible images to capture what could be the highest resolution views of 3I, Atlas, at perihelion. But there's uncertainty even here. Solar Orbiter's pointing is limited. It can only look in certain directions without risking damage from solar radiation. If 3I, Atlas's trajectory shifts even slightly from prediction by a degree or two, it could slip outside the spacecraft's safe observation zone. Mission planners won't know for sure until the day before whether the geometry will work. Then there's the James Webb Space Telescope, the crown jewel of modern astronomy. JWST can't look anywhere near the Sun. Its delicate infrared instruments would be overwhelmed by stray sunlight. But in the days after perihelion, as the comet recedes and the Sun-Comet Earth angle widens, JWST has been scheduled for a 6-hour observation block starting December 21st. Those observations will target the mid-infrared spectrum, heat signatures from dust grains, temperature structure in the coma, and organic molecules that glow most clearly in infrared light. The coordination required for all this is staggering. Each telescope has its own scheduling system, its own priorities, its own technical constraints. Getting them all to focus on a single target within a narrow window took months of planning coordination meetings across time zones, and in some cases emergency directors' discretionary time, the astronomical equivalent of pulling a fire alarm to cut to the front of the line. And it isn't only professional observatories. Amateur astronomers around the world have been mobilizing too. The Amateur Comet Observers Network, a loose collaboration of hundreds of experienced comet watchers, has built a shared database where anyone can upload images, brightness measurements, positional data, and even spectroscopy for those with the equipment. It feeds into a central archive that professionals can access in real time, a kind of living logbook written under night skies. During Comet Ison's approach in 2013, amateur observations provided critical early warning that the nucleus was disintegrating hours before large observatories confirmed it. Michael Jaeger, an Austrian amateur astronomer, who's photographed comets for 30 years, has positioned himself at a dark sky site in the Austrian Alps, specifically for the 3I Atlas campaign. His setup, a 12-inch telescope with a high-sensitivity CCD camera, rivals what professional observatories had just a generation ago. For objects like this, Jaeger said in an interview with Sky and Telescope, you need continuous monitoring. Professional telescopes observe for an hour, then move to another target. Amateurs can stay on one object all night, catching short-term variations that big telescopes miss. But even with all this coordination, all this technology, there are things we simply won't be able to see. The nucleus itself, for example, even Hubble can't resolve 3I, Atlas's nucleus, at this distance. A 2-kilometer object at 150 million kilometers appears only about 0.003 arcseconds across, like trying to see a basketball from 600 miles away. What we see is the coma, the vast cloud of gas and dust surrounding the nucleus, thousands of times larger and easier to observe. But the coma is only the symptom. The real story, the structure, the composition, the fractures or their absence, remains hidden behind a veil we can't truly penetrate. We also won't know the rotation rate with certainty. Light curve analysis offers hints, but without resolved images of the nucleus, we're inferring rotation from brightness changes carefully, imperfectly. A fast rotator would show regular periodic pulses. A slow spinner or a complex tumbler would be harder to characterize. And rotation matters for fragmentation risk. Spin too fast, and centrifugal force helps pull the comet apart. There are blind spots in the data. 2. No telescope watches continuously in every wavelength. Optical telescopes capture visible light. Infrared telescopes track heat. Radio telescopes trace molecular emission. Ultraviolet instruments reveal high-energy processes. To get the whole picture, you'd want them all, observing simultaneously, and that's impossible. There will be gaps, moments when something important happens, but only one or two instruments are watching, limiting what we can infer about cause and effect. Dr. Colin Snodgrass, who leads the European effort, put it pragmatically, we'll get great data, the best we've ever gotten for an interstellar object at perihelion, but we'll also be left with questions. That's how science works. You solve some mysteries and uncover new ones. The reality is December 19th isn't an ending. It's a beginning years of analysis, debate, modeling, and interpretation. The observations being made now could keep astronomers busy well into the late 2020s as they compare spectra with fragmentation models, test theories of planet formation, and argue over what isotopic ratios truly imply about 3I, Atlas's origin. But for now, in these final hours before perihelion, the focus is simpler. Watch. Record. Don't miss anything, because this is it, this one chance. 3I. Atlas will never be this close to the Sun again. After perihelion, it will accelerate back toward interstellar space, fading over months, eventually becoming too faint for even the largest telescopes to track. By mid-2025, it will be gone, lost against the background stars, headed back into the cosmic dark. But before it slips away forever, there are still questions that need answers. Questions not only about what 3I, Atlas is, but what it represents, and what it might mean for how common these visitors truly are. There's a moment in every major astronomical discovery when the data stops making complete sense, when straightforward explanations don't fit perfectly, and scientists begin to entertain ideas they wouldn't usually say out loud. Not wild speculation, they're too careful for that, but thoughtful what-ifs that press gently against the boundaries of conventional thinking. 3I, Atlas, has created several of those moments. Let's begin with the least controversial wild theory, the one that's actually appeared in peer-reviewed papers. 3I, Atlas might not be a comet at all, at least not in the traditional sense. When the Rosetta spacecraft studied Comet 67P up close for 2 years, one of its most surprising discoveries was just how dark the surface was. Not grey, not brown, black. The nucleus reflected only about 6% of sunlight, darker than charcoal, darker than most asteroids, one of the darkest objects in the solar system. That darkness comes from complex organic compounds, those tholins we mentioned earlier, coating the surface like a thin tar. But beneath that crust, Rosetta found something else. The nucleus was astonishingly porous. Its density was only slightly higher than cork. Roughly 70 to 80% of its volume was empty space voids, cavities, and gaps between loosely compacted ice and dust. It wasn't a solid iceberg drifting through space. It was more like cosmic foam, fragile, caverned, quietly precarious. What if 3I, Atlas, is even more extreme? What if its interior is almost entirely void space? A thin shell of ice and rock wrapped around a hollow core. That sounds strange, but it isn't as impossible as it feels. Dr. Nalin Samarasenia at the Planetary Science Institute has modeled how such structures could form during early planet formation. As dust and ice grains gather in a protoplanetary disk, they don't pack efficiently. They stick where they touch, building a skeletal framework with countless gaps, like a slow-growing lattice in the cold. Over time, more material fills in some spaces, but not all. The result can be a hierarchical structure, solid in places, hollow in others, with cavities ranging from millimeters to meters across. If 3I, Atlas, contains large internal voids, that could explain several puzzles at once. The October outburst might have been a cavity collapse, the roof of a subsurface chamber giving way suddenly, exposing buried volatile ice to sunlight. The irregular brightness variations could reflect sunlight seeping through thin sections and warming interior pockets at uneven intervals. Even the elevated carbon monoxide could make sense. CO ice trapped deep inside cavities would be shielded from sublimation, preserved through millions of years, while the surface slowly weathered away, leaving secrets intact until the sun finally calls them out. The catch is simple. A body full of pores is also a body full of weakness. Perihelion may not warm it kindly. It could spark a chain of collapses, where one hollow chamber fails and the next one follows, and the next, and the next. Picture a honeycomb under pressure. It doesn't snap in one clean line. It buckles, layer by layer, until there's no single solid heart left, only drifting debris and a memory of shape. And then there's the binary idea. What if 3I, Atlas, isn't one traveler, but two, a contact binary where two nuclei just barely touch, or a separated binary where a pair circles each other only a few kilometers apart? In the dark, those two centers could be like twin embers buried in ice. It happens more often than most people realize. Comet 67P, the Rosetta comet, was almost certainly a contact binary, two bodies fused into one silhouette, two distinct lobes, joined by a narrow neck, like a slow-motion cosmic rubber duck. New Horizons showed us in 2019 that the Kuiper Belt object Arakoth is also a contact binary, two small worlds that met gently and stayed together. It's the kind of merger that leaves seams, weak points, and pockets where volatile ice can hide. And several near-Earth asteroids are known to be separated binaries, with a tiny moonlet orbiting a larger primary, an invisible dance revealed only through careful measurement. For 3I, Atlas, a binary structure, could make the odd activity feel less mysterious. If the two components differ, one rich in supervolatile ices, the other more stable, they would answer the sun's heat in different ways as they revolve. The geometry changes hour by hour. One face is lit, the other is shaded. First one brightens, then the other, producing random swings in brightness and gas output that don't fit a simple single-body rotation model. Even the coma could look slightly lopsided as different vents wake in sequence. Petr Pravec, a Czech Academy of Sciences researcher who specializes in binary systems, has noted that roughly 15% of near-Earth asteroids are binaries. There's no strong reason interstellar objects should be different, he argued, in a 2023 review. If anything, gentle ejection into interstellar space might preserve binaries that more violent events would tear apart. A soft gravitational nudge could send a pair drifting outward without snapping the bond between them. The problem is confirming it from here. At 3I, Atlas's current distance, even Hubble can't separate two nuclei only a few kilometers apart. They blur into one point of light. The best test is exquisitely precise light curve work, measuring tiny rises and dips in brightness as the system spins. Researchers look for a telltale double-peaked rhythm, the subtle signature of two bodies alternately eclipsing and revealing each other, like clockwork hidden inside fog. Some teams say they glimpse hints of that pattern in the November data. Others call it noise. And if 3I, Atlas, truly is a weakly bound pair, held together by gravity only barely stronger than the tug of solar heating and tidal stress, perihelion could pry it open. One object becomes two tracks on the ephemeris, each fragment's coma trailing its own thin ribbon. Over the following weeks, those paths would separate, slowly, like two lanterns drifting apart in the same current. Now we step into slightly more speculative air, the artificial structure hypothesis. Before your mind jumps ahead, no serious scientist is declaring 3I, Atlas, an alien spacecraft. but a few researchers have noted that certain measured traits can, in principle, overlap with what an engineered object might resemble from far away. At interstellar distances, nature and technology can both present as silhouettes and spectra, and the data can be stubbornly ambiguous. In science, you're meant to weigh every hypothesis that can plausibly fit the data, even the uncomfortable ones. The argument begins with the first visitor, Oumuamua, an object with an unusual shape and a small, non-gravitational acceleration that standard outgassing struggled to explain. Several papers, including one by Harvard astronomer R.V. Loeb, suggested the acceleration matched a light sail model, a thin reflective sheet nudged by sunlight. Not proof, but a reminder that models compete, and sometimes the least intuitive curve can still trace the data. That doesn't mean it was a sail, only that, at the time, the model fit some aspects better than the alternatives. 3I. Atlas brings different oddities. Its barely hyperbolic orbit, a sodium emission line that hints at an unusual mineral mix, activity patterns that don't look like a typical solar system comet bursts, pauses, uneven jets. Could those together point to something non-natural? Beatriz Villarreal at Stockholm University, who studies unusual transients, framed it cautiously in a 2024 interview, emphasizing that unidentified is a category, not a conclusion. We should stay open to the possibility that not every unidentified object is natural. The universe is 13.8 billion years old. Civilizations could have risen and vanished countless times, and artifacts, if they exist, might still drift between stars, silent and cold. But extraordinary claims demand extraordinary evidence, and we don't have that for any object yet, including 3I, Atlas. The calmer explanation, and the one most scientists prefer, is that 3I, Atlas is simply a comet from a planetary system that formed under different conditions than ours, and its strangeness is the signature of that alien birthplace, not machinery. Sodium could reflect a parent star with higher metallicity, or minerals that lock sodium more loosely and release it more readily under heat. The orbit could be a statistical fluke. The activity could reflect chemistry we haven't learned to model well because our detailed sample comes from home. And yet, the artificial idea can't be dismissed with a single sentence. For one reason, we can't go there. We can't land, drill, or peel back the surface. We're reading it at a distance, like a message written in dim light, filtered through dust and glare, and the limits of our instruments. All we truly have are remote measurements, brightness, spectrum, trajectory. They sharpen with every night of data, but they carry limits baked in. A spectrum is a whisper, not a confession. From millions of miles away, you can't prove natural any more cleanly than you can prove artificial. Carl Sagan offered a guiding rule for moments like this, when wonder threatens to outrun evidence. Extraordinary claims require extraordinary evidence, and the absence of evidence isn't evidence of absence. So we shouldn't assume artifacts exist without a compelling reason, but we also shouldn't pretend the universe can't surprise us. For 3I, Atlas, the compelling reason would need to be unmistakable, something that survives every mundane explanation. A radio beacon, a perfectly geometric form in high-resolution imagery, acceleration that no natural process could plausibly generate. None of those have appeared. So the default remains, a natural comet, however unusual. Perhaps the most honest stance is the one voiced by Michele Bannister at the University of Canterbury. Our interstellar sample is still far too small, and strange may simply be what normal looks like in a broader galaxy. 3 objects, and that's it. You can't build reliable statistics from 3 examples. Maybe 3I, Atlas is rare, or maybe it's common, and we've simply been unlucky or lucky in what we've seen so far. That's the true wildcard. We don't know what we don't know. Each interstellar visitor widens our map of normal, and each one also opens new questions we didn't even think to ask. Oumuamua showed us shapes unlike anything we'd catalogued before, almost like a typo in the sky. Borisov showed us familiar comet chemistry can cross light years intact. And 3I, Atlas, is showing us something still coming into focus, right now, as the countdown slips into its final hours. Whatever it is, pristine comet, fragile rubble pile, binary pair, or something we haven't named perihelion, is about to make it speak under the brightest spotlight our system can offer. The telescopes are ready, observers are awake, recorders are rolling. A whole planet has, in a sense, turned its eyes outward. But once perihelion passes, once those critical hours close, and 3I, Atlas begins its long return toward interstellar space, what then? What becomes of the data, the questions, the careful watching? December 20th, 2024. Perihelion has come and gone. 3I. Atlas has survived its closest brush with the Sun and has started drifting back toward the outer solar system. But in a sense, this is where the story truly starts. The first question astronomers ask isn't, what did we learn? It's simpler, is it still there? Remember Comet Ison? On November 28th, 2013, it reached perihelion as a solid body roughly a mile across, bright with promise and fragile by nature. NASA's Solar Dynamics Observatory watched it approach, vanish behind the Sun's disk, and reappear as a faint smudge. For a few hours, hope lingered maybe that smudge would brighten as gases boiled off an intact core, a survivor limping onward. Instead, day by day, it faded into nothing, as if the Sun had erased it. The nucleus had been fully vaporized. What emerged was only a dispersing veil of dust, no solid center left to anchor it. So when 3I, Atlas, reappears from the Sun's glare on December 20th, and telescopes in Australia and South Africa lock on again, the first metric is brightness. If it matches predictions after accounting for the expected perihelion heating, then the nucleus likely held together, at least for now. If it's dramatically brighter, fragmentation may have exposed fresh surface area, expanding the active zones and boosting gas and dust. If it's markedly fainter, that points the other way, catastrophic breakup into pieces too small to stay vigorous, a comet that has become a fog. So let's walk through the possibilities and what each would mean. Scenario 1, clean survival. 3I, Atlas returns intact, a touch brighter than before, with no clear sign of splitting. The light curve relaxes into a more predictable cadence, like breathing settling after a sprint. Spectra show elevated production for a few days as the warmed nucleus begins to cool. Then activity gradually declines as distance from the Sun grows and the coma thins. Strangely, this uneventful outcome can be the most valuable. A single intact nucleus means the weeks of post-perihelion data describe one coherent object. We can watch how activity decays with cooling, species by species, almost like listening to different instruments fade out of a song. Water vapor, which sublimates easily, should fall quickly. Carbon monoxide, with its lower sublimation temperature, should linger, whispering longer into the dark. By fitting those decay curves, astronomers can infer the thermal gradient inside the nucleus, how deep perihelion heat penetrated, where warmth pooled, and how quickly it bleeds back into space. Yanga Fernandez at the University of Central Florida has spent years modeling comet thermal evolution, and he returns again and again to this cooling phase. In a 2022 paper on post-perihelion behavior, he emphasized that the cooling phase is where internal structure reveals itself. A porous nucleus full of voids cools faster than a dense solid one. A large nucleus holds heat longer than a small one. The fading activity curve becomes, in effect, a thermometer for the hidden interior, a slow diagnostic trace written in light. For 3I, Atlas, that would be unprecedented. No interstellar object has been followed through an entire perihelion passage and its cooling aftermath. We would be watching, in real time, how an alien comet responds to a quantified thermal shock, and those measurements would steady our models for decades, giving future visitors a clearer context. There's also the path through space. Perihelion doesn't rewrite the orbit dramatically at these distances, but it can shift it measurably. Outgassing jets act like tiny thrusters, imparting small pushes that accumulate, nudging the comet's path by fractions that only careful astrometry can see. By comparing 3I, Atlas's post-perihelion trajectory, to pure gravity predictions, astronomers can estimate the total momentum carried away by gas and dust, and that, in turn, constrains how much mass was lost, tightening the estimates of nucleus size and composition. Scenario 2, controlled fragmentation. 3I, Atlas, splits into a few large pieces, say 2 to 5 major fragments each, perhaps several hundred meters across, each with its own weakly glowing coma. The fragments remain close, within a few thousand kilometers, traveling on nearly the same orbit. One object becomes a small fleet, and each fragment becomes its own experiment. Do their spectra match, or do they reveal chemical patchiness inside the original body? Do their rotation rates differ, hinting the parent spun fast enough to shed material preferentially? Do some fragments flare more strongly, betraying richer volatile pockets, while others stay comparatively quiet? History says fragmentation can be extraordinarily instructive. When comet Shoemaker-Levy 9 broke into at least 21 pieces before striking Jupiter in 1994, astronomers effectively studied multiple cross-sections of the same object. Some fragments looked denser and darker, suggesting deeper origin, older material pulled from within. Others appeared brighter and fluffier, likely peeled from outer layers that had been processed and softened. The diversity revealed structure layering, gradients, internal variety. If 3I, Atlas fragments, each piece should cool at its own pace depending on size and composition, and those differences become clues that point inward. Tracking the fragments would be like assembling a slow CT scan of the original nucleus, reading its architecture from the behavior of its broken parts. There's also a practical advantage. Fragments can extend the observation window. A single intact nucleus may fade beyond reach by mid-2025 as it races outward, but a train of pieces can remain detectable longer, each one a lingering ember. Some fragments might still be trackable into late 2025, even into 2026, offering months of extra data. Scenario 3. Catastrophic disintegration. 3I, Atlas, falls apart into hundreds or thousands of pieces, most too small to track individually. What remains is a swelling debris cloud, like Comet Linear in 2000 or Ison in 2013, spreading into a thin, widening veil. It sounds like the worst outcome, yet it still carries science. First, the breakup itself sets limits on strength. We can estimate the stresses at perihelion, thermal, tidal, rotational, and if those exceeded the nucleus's ability to hold together, we learn what its material could not endure. We learn where it failed, and how quickly. For an interstellar object, that's a powerful constraint. Are alien comets built like ours, or do they differ in strength and structure? Second, debris clouds evolve in readable ways. Fine dust is pushed outward by radiation pressure, swelling into an expanding shell, while sunlight sorts particles by size like a gentle sieve. Larger chunks stay closer to the original orbit, drifting apart as tiny velocity differences spread them out. By measuring the expansion rate and morphology, astronomers infer the debris size distribution: how many boulder-scale pieces, how many pebbles, how much fine powder. Zdenek Sekanina at JPL has built a career on the mathematics of disintegrating comets, turning fading smudges into reconstructed histories. His models take the shape of a cloud and work backward toward a plausible nucleus. The spread pattern is a fingerprint. It can hint at rotation, fracture geometry, and whether the breakup was sudden or staged. For 3I, Atlas, that fingerprint would be one of the few ways to see an interior we can't resolve directly, an X-ray made of motion. A debris cloud might even grant a final gift: spectroscopy of freshly exposed interior material. When a comet breaks, deeply buried ice meets sunlight for the first time in millions, possibly billions of years, and it begins to sublimate immediately. The spectral signature of that interior could differ from what we measured before perihelion, like a new chapter revealed when the cover tears. Less weathered, more pristine, closer to the chemistry of the protoplanetary disk where 3I, Atlas, formed. In that case, NASA's JWST observations scheduled for December 21st would be crucial. Webb's infrared vision could map warm dust in the debris, measuring temperature patterns that tell us how recently surfaces were exposed and which grains were newly born to sunlight. Hot dust implies a fresh breakup. Cooler dust suggests fragmentation happened hours or days earlier, giving grains time to radiate heat away. And then comes the long game. No matter which scenario unfolds, intact nucleus, fragment train, or dispersing cloud, the hardest work begins after the watching ends. When 3I, Atlas fades, astronomers will be left with terabytes to sift, a quiet mountain of photons. That analysis will take years. Spectra must be calibrated and cross-checked against laboratory ice and dust measurements, then compared with chemical models. Light curves must be fitted with rotation and outgassing physics. Trajectories must be refined using every last data point to constrain mass and activity. Papers will follow, and so will arguments, and then better models. Conferences will fill. Graduate students will write dissertations on specific quirks of 3I, Atlas's behavior. Slowly, through the late 2020s, a consensus will form about what it was, where it likely came from, and what it taught us. Yet one question will remain beyond analysis, hovering above every conclusion. When will the next one arrive? How long until another interstellar visitor sweeps through our solar system, bringing fresh mysteries and fresh chances? Statistics hint we might see one every few years, But statistics built on tiny samples are fragile, and our sample is still vanishingly small. 3 points do not define a curve. We've confirmed 3 in 7 years. That could be the true rate, or we could have been lucky. The next might arrive in 2025 or 2035, or not until the next century. What we do know is that every single one matters. Every observation sharpens our methods. Every measurement prepares us for the next encounter so we can react faster and learn more. And that preparation, everything we learn from 3i, Atlas, may matter more than any single headline. Step outside on a clear night and look up. Every star you can see, scattered like quiet sparks, is a sun. Around many of those suns, perhaps most circle planets. Rocky worlds like Earth, and giants like Jupiter, and forms we haven't imagined. And beyond those planets, in the cold outskirts of each system, drift billions of icy bodies, comets, leftover crumbs of formation that never became worlds. Now consider the scale. Our galaxy holds something like 100 to 400 billion stars. If even a fraction host comet reservoirs like ours, the Milky Way contains trillions upon trillions of icy objects and gravity. Close stellar flybys, collisions, and slow orbital drift constantly fling some of them outward into interstellar space. The result is a galaxy filled with wanderers, objects like 3i, Atlas sliding between stars, carrying the chemistry of their birthplaces, moving so slowly that crossing even a small slice of the Milky Way can take millions of years. They're everywhere, and almost all are invisible until one passes close enough to a star, our star, to be captured and studied. Seen this way, 3i, Atlas, isn't a once-in-a-lifetime miracle. It's a sample, a single point from an immense population, and that's why it matters. It leads us to the panspermia question, the one that sits quietly at the edge of biology and astronomy. Panspermia is the idea that life, or at least the ingredients for life, might spread between star systems aboard objects, exactly like 3i, Atlas. We already know comets can carry water, ice, organics, even amino acids. When NASA's Stardust mission studied Comet Wild 2 material in 2006, it detected glycine, the simplest amino acid and a basic building block of proteins, evidence that prebiology chemistry can happen in space. That glycine formed in space, in the cold chemistry of a protoplanetary disk, before Earth even existed. The building blocks of biology aren't exclusive to our world, they're cosmic. Now imagine an interstellar comet, perhaps, ejected from a system where life exists, carrying not only organic molecules, but dormant microorganisms, tucked into micro cracks like seeds in stone. Bacteria can be astonishingly tough. Some endure radiation that would kill a human many times over. Others slip into dormancy for immense stretches of time, as if time itself pauses. Could microbes survive a multi-million-year voyage through interstellar space, embedded in ice, shielded from cosmic rays by meters of rock and frozen gas, with only faint starlight and occasional particle impacts as company? Gerda Horneck, a pioneer in studying extremophiles in space-like conditions, ran experiments aboard the International Space Station, exposing microbes to vacuum, radiation, and brutal temperature swings. Some survived for years, not every cell, but enough. Life, she concluded in a 2010 review, may be more resilient than we usually assume, more able to persist at the edge. If microbes can endure such travel, and if interstellar comets regularly thread through planetary systems like ours, then life might not be isolated to single worlds. It might be a slow, random galactic phenomenon, spreading wherever conditions allow. Earth's life could have begun here, or it could have been seeded by an ancient interstellar impact billions of years ago, long before anyone could notice the messenger, long before we had words for star system. 3i. Atlas won't answer that definitively. We're not going to detect life on it. We don't have the tools to identify biosignatures at this distance, and the odds that this particular comet carries organisms are tiny. But each interstellar object we study tells us whether the chemistry necessary for life is widespread, whether the same ingredients appear again and again. Are complex organics common? Are amino acids everywhere or rare? Do different star systems produce different chemical dialects? Or do the same reactions arise wherever the starting ingredients exist? The more visitors we measure, the clearer it becomes whether Earth's biology is a cosmic accident or an almost inevitable consequence of universal chemistry. There's also a more immediate angle: planetary defense. On February 15th, 2013, a roughly 20-meter asteroid entered Earth's atmosphere over Chelyabinsk, Russia. Traveling about 19 kilometers per second, it detonated around 30 kilometers up, releasing energy on the order of 500 kilotons of TNT, about 30 times Hiroshima. The shockwave shattered windows across the region and injured more than 1,500 people. It was a sharp reminder that space isn't empty and Earth isn't invulnerable. That object came from within our solar system, on an orbit we might have detected with enough coverage. Now imagine an Oumuamua-like object, but larger and aimed at Earth, arriving without the warning we've trained ourselves to expect. By the time we noticed it, it could be moving around 26 kilometers per second, arriving from a direction we weren't watching because we don't expect threats from interstellar space. We'd have weeks, maybe months, not years. Our current defense strategies, careful tracking of near-Earth asteroids, and long-planned deflection missions assume time, repetition, second chances. Interstellar visitors break that assumption. Kelly Fast, who manages NASA's Near-Earth Object Observations program, highlighted this after Oumuamua. Our systems are optimized for objects in bound orbits around the Sun, objects that come back and can be refound. Bound objects return again and again, so missing them once isn't always fatal. Interstellar visitors don't offer a second pass. You either catch them on the way in, or you miss them entirely. The good news is that the odds of an interstellar impact are vanishingly small. Space is vast. Earth is tiny. Even with trillions of wanderers drifting through the galaxy, the chance of one striking Earth in any given year is essentially zero. But essentially is not the same as absolutely. Understanding their composition, structure, and behavior helps us prepare for the unlikely scenario in which one does matter to us directly, and helps us know what kind of response would even make sense. If 3I, Atlas, is porous and fragile, a similar impactor might break up high in the atmosphere, reducing ground damage. If it's dense and coherent, breakup is less likely, and more energy reaches the surface. These aren't idle thoughts. They're parameters that feed into impact simulations, and simulations become decisions when minutes matter. Simulations that shape evacuation planning, deflection strategy, and risk assessments. And then there's something deeper still: perspective. For most of human history, the night sky felt static, like a ceiling rather than an ocean. The stars looked fixed, eternal, unchanging. The planets wandered, that's what planet means, yet they stayed within predictable bounds. The cosmos seemed orderly and steady. Then telescopes and mathematics revealed the truth. Everything moves. Stars drift through space at hundreds of kilometers per second, and even stillness is motion too slow for our eyes. Galaxies collide and merge over billions of years. The universe expands, carrying distant galaxies away faster than light can cross the growing gulf. Nothing is truly static. Nothing is truly permanent. And now we've confirmed what astronomers long suspected. The space between stars isn't empty. It holds wanderers, cold and ancient, objects flung from distant systems, carrying the chemistry and history of worlds we will never see. 3I, Atlas, crossed the void for millions of years, survived its encounter with our sun, and will travel millions more, perhaps to brush another star system someday, perhaps to drift forever through the cosmic dark, a quiet shard of someone else's beginning. We are witnesses to a single, delicate chapter of that journey. For a few weeks in late 2024, this visitor passed close enough to study, and we turned every telescope we could toward it, gathering data that will echo through years of analysis. We asked questions, we measured, we learned at least a little about what lies beyond our neighborhood and about ourselves as observers. And that act, observing, measuring, trying to understand, has its own quiet grandeur. We are the species that looks up. We notice the wanderers. We trace their paths and wonder where they began. We build instruments that extend our senses, catching light our eyes can't register and distances our intuition can't hold, translating the sky into numbers and stories. 3I, Atlas doesn't care that we're watching. It isn't performing for us. It's simply obeying physics, responding to gravity and heat and radiation according to its structure. But we care. We're curious. And that curiosity, the urge to understand the universe, not only because it's useful, but because it's there, may be one of the most remarkable human traits, the one that turns darkness into a map. Carl Sagan, in Pale Blue Dot, reflected on Voyager 1's distant image of Earth, all our lives unfolding on a tiny speck suspended in sunlight. The thought is gentle and unsettling at once. That perspective, seeing ourselves as small and temporary within something immense, doesn't diminish us. It elevates us, because we are the dust that learn to look outward. We're the ones who ask questions. 3i. Atlas reminds us our solar system isn't isolated. We're part of a galactic ecosystem, connected to distant stars by these wandering messengers. Every few years, one passes through. Each one teaches something new, expands understanding, and raises questions we didn't know to ask, like doors opening in a hallway we thought we knew. And somewhere out there, right now, the next visitor is already on its way. We don't know when it will arrive, we don't know what shape it will have, or what mysteries it will carry. But we know it's coming, because the galaxy is old, vast, and full of worlds, and some fraction of those worlds send their orphan children into the deep, into the long night between suns. When the next one arrives, whether in 2025, or 2050, or 2000, 100 humanity will be more prepared. Better telescopes, sharper sensors, more refined models. We'll have learned from Oumuamua, from Borisov, from 3i, Atlas. Each encounter improves our methods. Each measurement deepens our understanding. We're learning to read messages written in ice and rock, sent from star systems so distant their light takes decades or centuries to reach us. We're learning the language of the cosmos, one visitor at a time, and each time we decode a little of that language, turning faint photons into knowledge, we take part in something larger than ourselves, like listeners catching fragments of a song from across the sea. We are the universe, in one small corner, trying to understand itself, and that may be the most important story of all.